Welcome everyone to the third and the final day of our workshop. So what we are trying to do, as you remember, in this over these 3 days, to kind of look at 3 very important contexts of social media, of transportation, and today of healthcare delivery, that kind of all have in common this fact that kind of to really understand them and make progress on them, we not only need to understand the AI part, but also we need to understand the human part and the system part and how all of these things and incentives play together. And in some ways, I would say that healthcare is one example that really brings all of these aspects, aspects to the light. And again, we are really lucky to have the speakers that can really shed some light on some of these complexities and the difficult problems there. So we have 3 speakers today and 3 speakers panelists. So the first panelist is Marzyeh Ghassemi. So Marzyeh is currently a professor at Toronto, but soon she will move to a place called MIT, and some of us are extremely excited about that. So we are looking forward to have her there. So clearly she's making the right choices. But what Marzyeh is doing is essentially kind of looking at healthcare and essentially how ML can influence healthcare, but not kind of looking only at the obvious way, but she actually tries to look into the nooks and kind of a bit deeper, deeper aspects of it. In what way deployment of ML in healthcare, like what kind of opportunities it brings, but also what kind of dangers it might bring up. So she will have a very nice perspective to give us today. So that's the first speaker. The second speaker today is Senthil Mullainathan. So Senthil is economist, and he did really amazing things in economics, in particular in behavioral economics. But what he's doing over the last few years, he's really focused on healthcare and kind of bringing on one hand this economics point of view on healthcare, but also really trying to understand it as a system. And again, we believe that this will be a very, very interesting perspective over here, and he's doing, again, a lot of interesting stuff there. I do hope that at one time he will be a colleague at MIT, but for now I can only hope. And our third speaker is Colin Schultz. And Colin he's my colleague at the EECS department, and Colin comes from yet another angle. So he actually has a clinical background, so he actually is a doctor and he is kind of on the ground, but he also thinks deeply how to understand certain aspects of our physiology using machine learning and kind of what opportunities but also dangers arise there. And again, that's the perspective that he will be able to contribute. So these are the 3 speakers, and again, quite different complementary perspectives. And now the question is who should be leading this, this discussion? And we couldn't have none other than Shankar Shastri. So honestly, this is a difficult introduction to make, because honestly, I actually try to understand what Shankar is doing, and I realize is what he's not doing. So he's doing everything. So he's jack of all trades. He really thinks very deeply about how essentially, computer science, computation, and data kind of influences different systems that, the technical systems that are deployed in the real world. And kind of, he's one of the, people who thinks a lot about this, about where we are and where we should be. So he will provide a wonderful perspective as kind of leading the discussion and, asking all the questions. So without further ado, I will just pass the baton to Shankar, and he can take over the session.
Thank you. And Alex, you yourself, I have to say, let me thank the 3 organizers of this workshop, Asu, Alex, and Saurabh, for putting this together. It's some of you may not have been there on the other 2 days. I think that it's a pretty ambitious workshop. They have really taken upon themselves the idea of trying to delineate the challenges there are of developing a science and technology for these systems, these digital, what we're calling digital transformation, which is really taking data from multiple IoT sensors, wireless sensors, even wired sensors, and then analyzing that and coming up with new mechanism design. And I think that they deliberately chose this format, which is a really innovative format, of having a few short set point talks followed by a discussion format. And, I hope you'll get to not only hear them, but talk about this. And I will, let me get people started. Let me just say a little bit about AI and machine learning. One of the sponsors of this institute is Microsoft, and actually our corporate sponsor at Microsoft is Eric Horowitz. And Eric Horowitz, actually, when he heard about this, he said, I cut my teeth on the system at Stanford called MICIN, which was really about using AI to do diagnostics in the Stanford Medical School. Of course, as some of you know, it had, there's the days of expert systems and so on and so forth. And, I think that the use of AI machine learning to really sort of change healthcare, I think we really, as a society, wanted this. And I think we have made numerous starts, some of them false starts. But I think it's really, the pandemic has really told us that it's critical to think this through. And I was telling the panelists before we went on the air about the book by our colleague from the Salk Institute, Eric Topol, who wrote a book recently, a popular science book called Deep Medicine, where he held out the prospect that having AI, really deep learning and machine learning, will really free up clinicians to spend more time healing and caring for patients, and sort of this the social and the behavioral dimensions of what this has as a potential is really, really important. And so I hope we can talk about this. And we said all these things about MIT, but let me say the sort of bombshell announcement that MIT made yesterday. They announced that the Broad Institute will be launching a new initiative on AI and medicine to be funded by the Schmidt Foundation, Eric Schmidt and his wife. And anyhow, so it's a real pleasure to see MIT also step out smartly in this direction. Okay, so that's let me start up by introducing. Well, I think you already heard the speakers. Marzyeh, the floor is yours.
All right. So thank you for inviting me. As Alex very eloquently introduced me, I am Dr. Marzyeh Ghassemi, and I am currently at the University of Toronto, but I'll be moving to MIT this summer, actually. And I'm going to talk to you a little bit about why I think models should not explain themselves. And if you know me at all, or have maybe taken a class from me or heard me talk, this is a particular pet peeve of mine for several reasons, but I'll go through them. So I think the first thing to establish is that machine learning really is in the wild at this point, right? So it's not as if we are in a space where we're thinking about how algorithms and models can be used in a clinical setting in medicine. They're already being used in machine learning models are already being used in medicine. We've had threshold-based alert systems that have been used for decades in acute care. And so it's not as if this is a new thing, but we are certainly talking a lot more about machine learning in medicine recently in the past couple of years. And the reason why I think is this lovely figure actually from Eric Topol's paper, which is we now have state-of-the-art performance, meaning these methods are performing at or above humans across the range of the human lifespan. And so we can define many clinical tasks that we might want a model to be able to perform. And we now have models that can do those things either as well as or better than humans. And I think that's really flipped the conversation and turned this into it's no longer a calculator that I'm using. This is now something that could really augment a human, possibly. But correspondingly, there's been a lot of concern, as you may have heard, right, about, well, what's in those boxes, right? We have all of these really high capacity models that have led to great performance across these different sort of predictions, but really what's under the hood, what's going on in there. And I really want to emphasize a conversation that has come up again and again in sort of this intersectional community, which is getting to trustworthy AI, right? So all of these criticisms about it's a black box, what's in the box, it's bad for business, they're really about, do we trust these models that are doing so well? And so I like to bring this back a step and say, well, why do we think we want trustworthy models in this space? So my own opinion on this is that we want trustworthy models because there's a huge interdisciplinary mismatch in expertise and expectations, right? We have a group of people who are often developing algorithms or models for problems in a space that they may not understand all that well, right? So you could have a clinician say, we've really been struggling with this problem for years. And a computer science student could say, well, you struggle no more, I'm here with my algorithms. And then 6 months later, or a PhD later, they could say, wow, this is actually a really hard problem. And of course, the people who are in the domain actually doing the work around that problem know that. And so I think because there is this sort of mismatch often, we've come to this space where we say, well, we don't want you to just throw something over the fence that we don't understand in this domain. We want it to be trustworthy. And there's many ways of defining trustworthiness. I'm going to focus on explainability because it's a very popular sort of both technical direction and maybe philosophical direction that has been brought up in the machine learning for health community. So the first thing I want to say is I'm not worried about whether we can get people to trust explanations. We have some really good work by roboticists like Iona Howard that have shown us that humans tend to actually overtrust robotic systems in a couple of scenarios. And those are scenarios where the person believes that a robot can perform a function they cannot, or the expectation is that the system is going to mitigate risks. And we have both of those in medicine. An MRI machine can do a function that I cannot. And so I have to trust that it's doing well, conditioned on the fact that it's well calibrated and serviced regularly. And often we have these provider order entry systems that try to flag when something seems inappropriate within a billing system or within an electronic healthcare record. And so both of these situations exist to some extent already in medicine. And I want to bring up a paper that I thought was very interesting by a colleague where I was talking to him about, well, maybe we don't have this problem because doctors are experts and they're really trained to such a high extent to be experts in a particular space. And he said, well, we did this experiment because this was like step one in our project. We just wanted to show that we could generate chest x-rays that were good enough to fool doctors. And then we had a whole set of things we wanted to do with those synthetic chest x-rays. But he had this sort of intermediate result on his very first AIM that was really intriguing to me. So he found that some doctors, and 50% here means that when the doctors are looking at the images, they can't tell whether the image is GAN generated or real. So they know better than chance, right? As they're looking through these images, half of the time they get it right, half the time they get it wrong. And that's where we expected it would be, right? Around that middle line, because these are good images that are being generated by the generative adversarial network. But what he found is that some clinicians actually favor GAN images. And those are users whose dots are above this line. And some clinicians favor real images. And those are dots that are below this solid line. And so again, here, I think the issue is we don't really know how humans are going to respond even to just synthetic data, let alone alerts, alarms, advice that appears to be very intelligent. And so I want to walk you quickly through an experiment that we recently published, where we said, okay, well, in health, it's really about human decision-making. And ultimately, we want to have improved care. So we want to figure out, how does advice impact both expert and non-expert clinical decisions? And what role does the accuracy of that advice play? Especially if we tell you it's from an AI, it's not, this is all human advice. A radiologist made all of this advice, or we tell you it's from a doctor. So do you interact and think about the advice differently if you think the source is different? So we designed a pretty simple experiment where we showed x-rays to either radiologists, those are our experts because this is a lot of what they do, they evaluate x-rays. And then we also evaluated non-experts. So these are people in internal and emergency medicine, IM, EM doctors who see x-rays, but it's not, really the special thing that they do most of the time. And we varied two things. So we varied whether the advice was accurate or inaccurate. And if it was inaccurate, it was plausible. It wasn't something crazy. We also varied the source of the advice that we reported. So all of the advice is the same. It's not like we had different accurate AI advice or human advice. It's all the same, made by us. We just said it was from an AI or said it was a human. And we measure two things. We measure how people are rating the advice they get and how it changes their behaviors. And what we found, I thought was really surprising. So we found that radiologists actually rate AI advice as much lower quality than human advice, even though it's the same advice, right? If they think it comes from an AI, these experts are saying that it's lower quality. And that's not something we see in the IMEM doctors. However, there is no significant difference in the clinical accuracy of either experts or non-experts under the two advice types. And so you can interpret this two different ways. You can say, well, it doesn't matter what the source of the advice is. And the way we were thinking about it is, well, physicians across expertise levels are really failing to dismiss the incorrect advice, whether it's from an AI or a human. And what that means is, you can see up here for the experts, they generally have a better diagnostic accuracy, right? So if I draw a line up here, right, and say this is the threshold of a good diagnostic accuracy, more experts make that cutoff. But if I go down and look at the IMEM doctors, fewer of these doctors make that sort of accuracy bar cutoff when they see these 8 cases. However, we see a similar proportion of doctors that are susceptible to this bad advice. And so if a radiology participant 60 has only blue, that means, and no red in their vertical bar, that means every case they saw with incorrect advice, they got wrong. And so they anchored to this incorrect advice and they weren't able to escape it, even if we said it was from an AI. And we have a similar proportion of expert and non-experts that are really fooled by incorrect advice and are susceptible to it. And this is really scary for me as somebody who does machine learning models. And it's not just us who have investigated this kind of interaction. So there's this really nice paper that came out in 2020 about human-computer collaboration for skin cancer recognition. And buried in one of these sub-figures is what I think is the most important figure of the paper, which is showing that if they give these doctors, so most of the paper, this is a summary over here, we find good quality AI-based support of clinical decisions, improves diagnostic accuracy. That's great. What they find is that if they give the wrong AI predictions, the decrease in the accuracy of the clinicians is significantly worse than the potential benefit if the model predictions are correct. And so for me, this really, takes us out of this technical space where we're thinking about models, right? And how good can I get my model? We know models will be wrong sometimes. There's no way to make a perfect model. And so now the question is, what do we do when the model is not perfect? How do we get humans to use it appropriately? And so one of the things that has been proposed time and time again in medicine specifically is explainability. Well, why don't you just get a model to explain itself? And I want to say explainability is not a panacea. And I think there is good evidence that it might make the problem worse. What I mean by that is there's really good recent work showing that the interplay between machine learning and human decisions is not benefited by clear models. So this work was looking at rental prices in the New York housing market. And what they found is that there's no significant improvement in the degree to which people can follow the predictions of a clear model with few features compared to other experimental conditions. And the other experimental condition is a black box. And so, for instance, they found that models with more transparency actually hampered people's ability to detect when there was a serious mistake. Like, for example, when there was an apartment with a particular configuration, like instead of having 5 bedrooms, 2 bathrooms, it was 5 bathrooms, 2 bedrooms. That unit, if a black box said it should go for a really high rental price with no explanation, humans said, no, that doesn't sound right. We think it should be lower. But if the model showed sort of its explanation of, look, well, I just counted up the rooms and this is a large number of rooms, then people disproportionately tended to agree with it and not detect this more serious mistake. And so I think models that are more transparent can make people feel like their choice is good, and therefore they don't do a more aggressive audit. And you might be saying, well, that was, the New York housing market and your experiment with x-rays, that was simulated. It wasn't in a real sort of clinical setting, where we think that decisions about routine care should be justified by evidence or in evidence that exists. But actually, medicine is a constantly evolving science where often procedures tend to get changed or practices tend to get redefined as we understand better what actually works well. So for instance, there was a great study that showed that about 400 routine practices in the past 10 years of top medical journals like JAMA, Lancet, New England Journal are these, medical reversal studies where a practice that people commonly do, a routine practice, is found to be wrong or lead to poor outcomes for different populations. We also, I think importantly for machine learning, where often we're looking at past examples of things as a good demonstration space for what we should do in the future, we don't audit doctors regularly in North America or in many countries internationally for accuracy or performance, right? They are regulated similarly to the way that lawyers are regulated, where there is sort of a self-policing mechanism or there are state medical boards, and you have to be essentially reported enough and your colleagues and peers have to agree that you are performing poorly. There's no sort of federal agency that's auditing whether doctors are consistently underdiagnosing or misperforming on certain people or certain classes. And finally, there's really good research that's come out recently that's shown that individual doctors, just like all humans, can have really strong preferences. And that can be both about the patients that they see and the treatments that they give to patients. And so that variance means that we're still in this space where differences in judgments are going to make a huge impact. So there are some arguments that I've been given for explainable models. I'm going to go through them briefly and say why I disagree. But the first one I don't actually disagree with, which is if there is a principle or a regulatory standard, like with GDPR, that says you need to fulfill a certain class of explanation or meaningful information, then that should definitely be followed. I think my only comment is we as a community need to really empower our regulatory agencies to do this appropriately and rigorously, because it's really hard to do this without expertise in the domain. A very, very common thing that I see on research papers that I review about explainability is it's really necessary in high-risk situations. So experts like clinicians, they need explainable AI models because these are high-risk areas and they need to understand what's going on. So I think this is not correct. And that's because I don't think we just need explanations or transparency in all settings that are high risk. I think the reason you would want some sort of explanation is when a clinical opinion differs significantly from the predictions that we have. That doesn't mean that clinicians generally care about how a model works, just like most clinicians don't understand in great detail how an MRI machine works or how lab blood gases are calculated or how even a digital scale works. Most of us don't. We don't understand all of those details, but we trust a process. I don't think that means that we need to build simple models for the sake of transparency. That could mean that what we need to do is understand when to rely or reject model outputs. We need notifications about what populations a model might work well on or fail on. And we need to include limitations of the data that the model is trained on. There are some good technical options that we can explore. And so common things that people do are post hoc explanations. these are only useful if they are consistent. And I want to say consistency in this, I am defining that as different model behaviors get different explanations, and the same model behavior gets the same explanation. And both attention-based models and saliency maps, which are very popular in imaging, are not, the vanilla versions of those are not consistent by definition. There are fixes that have been proposed, like competition-based all pixel versus all pixel maps. But just as they are commonly used, those are not consistent. I also think that interpretability counterintuitively just doesn't help with robust classification under things like attack. And so common post hoc explanation methods like Lime or Shapley, they don't work well for creating a more robust classifier. So now that I've told you all of these reasons why maybe you don't want to use explanations or post hoc justifications, let me show you how I've used them. Just to be clear, everybody uses these, right? Especially when they're developing. And in our case, we actually wanted the clinicians we were collaborating with to be able to look at the different parts of the model or the data that the model was using and see that they were contributing different kinds of information for predictive tasks. So here we were looking at intensive care unit patients. We had about 35,000, and we wanted to take all of their data. So these are clinical notes, vitals, labs, static variables. And we wanted to try to predict several different things. In this case, different kinds of interventions, both aggressive and less aggressive interventions in the intensive care unit. And I'm going to focus on what we did in deep neural networks, both recurrent and convolutional, because those are most often called black box models. And so here we did feature level occlusions where we removed certain kinds of data from the model and then said, now predict as well as you can. And we found that, for example, physiological data like pH levels, sodium, lactate, those are really important for predicting ventilation onset, right? Who's going to need a ventilator? But if we look at what's important for less invasive interventions like a fluid bolus, there it seems like the text that we are getting from topics actually is more important. You can also try to target these convolutional filter trajectories to try to understand what are the most and least activating trajectories looking like in the models when we are predicting things like need a ventilator. You can also do transparency through what I call natural outputs. And by that, I mean, the reason you want an explanation is often because the end product is not a metric that you're used to using. And so if we just deliver the thing that you're used to using, maybe we don't need to explain the thing we deliver. So one example of this is creating reports from clinical images. So I had a collaborator who wanted us to automatically generate radiology reports from chest x-rays. And the issue here is that this is not like image subcaptioning where you're supposed to talk about what's in the image, like the girl in the pink dress is jumping in the air. You have to first predict what you might want to talk about in the report and then confirm or deny that that thing is there. So in the example, there's no focal consolidation, effusion, or pneumothorax. This would be like saying, it is not the winter, there are no helicopters, and the girl in the pink dress is jumping in the air. And so here, because we need to first predict the topics and then conditionally generate sentences, we actually used a reasonably aggressive set of architecture to do so, right? So first we go from an image via CNN to this embedding space. Then we use the RNNs to predict these topics that we will need to conditionally generate sentences on. Then we generate the more diverse sort of text within those topics with a second RNN. And here we really wanted to make sure that what we were generating wasn't just human readable in a natural language sense, but was also clinically accurate because we wanted it to be potentially useful. And so we made sure that we are enforcing this idea of clinical coherence, where negation matters, where you saying that somebody has a particular disease that matters for the scoring of the model. And we found that by doing that, we were able to outperform state-of-the-art methods in both readability and clinical accuracy. And so again, really what we're performing best on here is disease accuracy. The natural language is a little bit better, but the disease accuracy is what's being improved. And the final thing I want to say as an option in this middle space is that really what we want in health is we want to make sure that there's transparency in the entire process. So it's not just the algorithm, it's also the embodied data that we're using. And so there are some really good resources that have been released in the past few years to try to understand not just model outputs. So I'm thinking about data sheets for data sets or model cards for model reporting, but also other big picture tools to try to move us from working towards transparent models to transparent processes, which I think is more important. The last thing I want to go through quickly, because it's a sort of last mile thing that is often said, is, well, black box models could really create, increase, and propagate biases. And this is true, it's fair. But bias is already part of the clinical landscape. It's not that machine learning algorithms hate minorities and minoritized people and want their healthcare to be bad. It's that minorities and minoritized people have had really bad healthcare. And so models pick up on that because they're often trained on current knowledge or historical interactions. And so there is a big question about how machine learning should interact with fairness and health. I think audits are one way that we can try to ensure that our models are fair. And in my mind, this is not something that only fairness researchers do. Everybody should be auditing model performance to make sure that there aren't, for example, in this case, significant differences in model accuracy across different race, sex, or insurance type. But I also want to caution that this can be very, very tricky. So for example, if you take popular transformer models, right? These are contextual word embeddings that are publicly available, anybody can use them. And so in this case, this is CyBERT, which is trained on PubMed abstracts. You can give it a prompt that is taken from real electronic healthcare records. Blank race patient became belligerent and violent, sent to, and ask it to fill in the blank. And it'll fill in that Caucasian and white patients should go to the hospital, but African American, and Black patients should go to prison. And again, this is not trained on the trash of the internet. It's not Reddit, right? These are PubMed abstract. This is CyBERT. And so these biases are really deeply embedded, and it's not one simple audit that's going to reveal them. We really do have a sort of need to go through an ongoing process that requires improvement across many considerations. There's no simple fixes to do ethical machine learning in health. So we really need to engage on many levels as a diverse set of stakeholders. So that's all of the arguments that I wanted to cover. I wanted to quickly say, I'm actually very positive about how machine learning can help improve care and practice. And that's because right now we're in a situation where a lot of doctors are burnt out. This is a pre-pandemic number, and a lot of them feel like they don't have time to be empathetic. Again, this is a pre-pandemic number. Given that, we don't want to copy poor treatment decisions or propagate incorrect assumptions or design new biased risk scores or models. We do want to improve processes that exist but are faulty. I often cite this study, which shows that a patient's probability of heart attack survival is actually different if you are male or female. And that effect is driven by increased mortality when male physicians treat female patients. And there's this quote that says, well, mortality rates actually decrease when these male physicians are either practicing with more female colleagues who are probably telling them, you should notice this thing that you're not noticing in only your female patients, or if they've treated more female patients in the past. So this means there really are opportunities for us to improve collaboration between models and clinicians, because the ultimate goal is to improve the humans that are providing the care. So in summary, I think explanations and transparency are very important when we debug or audit models as researchers and collaborations, but it's unclear to me how expert or non-expert end users can or should incorporate them. I think they cause over-reliance in many domains, and they have been shown to reduce our audit propensity of decisions. And we know that biases that can be created, increased, or propagated should be tackled, but we need to address this with aggressive audit standards and also by an ongoing process of investigation in the machine learning pipeline. And I think this will help us move towards learning that optimizes for improved human care, because that's ultimately who is delivering this care. This is work that's been done by a fantastic team of students, collaborators, and funding sources that have supported this. And I think there are good ways to move from this research to creating actionable insights in human health.
Fantastic, Marzyeh. That was a lot to chew on, but let's not take. There were like 1,000 questions I alone had, but let's sort of hold out till we till after the all the speeches. That was wonderful. Okay, Cynthia, should we get you? Nice talk, very nice talk.